Hi everyone, for today's lesson we are going to learn about arithmetic, geometric, and neither sequences. We're going to be writing explicit formulas for all of these sequences. But before we get started with our actual lesson, I would like you to please do this really quick warm-up. And for our warm-up, I would like you to please factor x cubed minus 4x squared minus 10x plus 40 and 5x to the fourth power minus 4x squared minus 1. So go ahead and take a moment, pause the video, factor each of these, and then restart the video. Let's see how well you did when you restart it. All right, so hopefully you were able to notice that the first problem is going to be one of those factoring by grouping problems, and that's where you put parentheses around the first two terms, change the middle sign to a plus negative, and put parentheses around the second two terms. X cubed and 4x squared have in common an x squared. The leftovers is x minus 4. Plus negative 10x and positive 40 have in common a negative 10, and our leftovers is x minus 4. So our factorization is going to be x squared minus 10 times x minus 4. For number 2, I'm going to split this trinomial apart into two parentheses. I'm going to split apart the 5x to the fourth power into a 5x squared and an x squared. And I know that the only way for me to get a 1 is to put a 1 in each position. And I want a negative 4x squared, so that means that I want to make 5 times this one negative, and I want the middle one to be positive, because 5 times negative 1 is negative 5, and negative 5 plus 1 is negative 4. Now this parenthesis right here is a dot, so it's a difference of two squares. So my final factorization is going to be 5x squared plus 1 times x plus 1 times x minus 1. So hopefully you did well on this factorization. If you did not do well, please make sure that you email me, because obviously factoring is going to be on your next test, so the Chapter 12 test. So now we're going to be writing explicit rules for neither sequences. So for arithmetic sequences, we know that arithmetic sequences are written as a sub n is equal to d times n plus b. And this is a linear function. We know that geometric sequences, when we're writing the explicit formula, it's related to exponential functions, and that is written in the form of a sub n is equal to a sub 1 times r to the n minus 1 power. So that represents your arithmetic and your geometric formulas. Those are your explicit formulas. However, just like with all neither sequences that we've been dealing with, neithers, we don't really have a formula for it. It just depends on what you see. It depends on what's going on. So you really have to think. So here's some tricks. Look at connections with the position number. Look at perfect squares. Look at perfect cubes, factorials. Try to see if there's something that where you're adding the same number and then maybe squaring something, or adding the same number and then multiplying by something. There's going to be a lot of things that you really just have to look at it and see if there's anything that you notice, and then write a rule that you think could work. What's really cool though about explicit formulas is that you do not need to know what term came before in order to find the next value. So let's go ahead and look at A, B, C, and F. The others we will do in class when I see you guys next. So looking at letter A, we have 1, 4, 9, and 16. Hopefully, all of you guys are able to look at this problem and say, okay, well, I know that 1, 4, 9, and 16 are all perfect square numbers. And that is absolutely true. We know that 1 squared is equal to 1, and 2 squared is equal to 4, and 3 squared is equal to 9, and 4 squared is equal to 16. So how can we incorporate the 1, 2, 3, and 4? Well, 1 is in the first position, 4 is in the second position, 9 is in the third position, and 16 is in the fourth position. So what we're doing in this formula is, in order for you to come up with your term, a sub n, that is equal to the position number that it's in squared. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And that's your rule. So whenever you are doing these problems, I would like to write down A, G, and N. So what A, G, N means is look to see if it's arithmetic. Are you adding the same number each time in order to get to the next number? If the answer is no, cross it out. Are you multiplying by the same number each time to get to the next value? If not, cross it out. That tells you that this is a neither, and in this case, it's a neither situation. You might have been able to see that it's a neither situation just by the fact it was perfect squares. So that's just a trick to help you with writing these formulas. All right, let's go ahead and look at letter B. For letter B, I have 2, 4, 6, and 8. Well, I know that to go from 2 to 4, I'm going to add 2, and to go from 4 to 6, I'm adding 2, and to go from 6 to 8, I'm adding 2. So in my arithmetic, geometric, or neither, because I am adding the same number each time in order to get to the next value, this is arithmetic. So it's not geometric or neither. So since this is arithmetic, I'm going to be using my arithmetic explicit formula. And so in my explicit formula, I need to identify what my common difference is, which in this case, my common difference is 2. And then I need to find my B value. So what I'm going to do is come up with an ordered pair. You can come up with any ordered pair that you would like. I'm going to work with the ordered pair 1, 2, because I think that it's the easiest ordered pair to work with. And how I came up with that ordered pair is 2 is in the first position. I could have worked with 2, 4, 3, 6, or 4, 8. Any of those would have been absolutely acceptable. Now I'm going to find what my B value is. So I'm going to plug that into the formula. A sub n is equal to D times n plus B. And A sub n, that's going to be equal to 2. And n is going to be equal to 1. So I'm going to write 2 is equal to 2 times 1 plus B. 2 times 1 is 2. So I'm going to subtract 2 on both sides. And when I do that, I end up with 0 is equal to B. So therefore, my answer is going to be A sub n is equal to 2 times n plus 0. Or, to clean it up and make it a little bit simpler, it's going to be A sub n is equal to simply 2n. And that is your answer. Let's go ahead and look at letter C. For letter C, we're going -3, 9, -27, 81. So I can tell that I'm going up by multiples of 3, but it's a little bit different. I know to go from -3 to +9, I'm multiplying by -3. And 9 times -3 is -27. And -27 times -3, that is equal to 81. So is this arithmetic, geometric, or neither? Since we're multiplying by the same number each time in order to get to our next value, we have ourselves a geometric sequence. So when it comes to geometric sequences, we're going to be writing geometric sequences in the form of A sub n is equal to A sub 1 times r to the n minus 1 power. So in order to write our formula, we need to know what our first term is. In this case, it's -3, and we need to know what our common ratio is. In this case, it's -3. So our formula is going to be A sub n is equal to -3 times -3 to the n minus 1 power. And that is simply your answer. But now that I'm looking at it, there's something special going on here. So this is actually considered a special case. So what I'm about to do is a little weird, and this is not going to necessarily be true for all of the other geometric problems that you see here. Do you guys see how we're multiplying by -3, and this is -3, and these two numbers are exactly the same? So whenever you have two powers with the same base, we always add the exponents. Do you guys remember doing that? Well, whenever you multiply two powers with the same base, we're going to add our exponents. So this really means A sub n is equal to -3 to the 1 plus n minus 1 power. We're multiplying two powers with the same base, so we add our exponents together. 1 minus 1 cancels out, so our real answer is A sub n is equal to -3 raised to the nth power. This is a special case. Our geometric Sequences will not turn out to be like that every single time. It'll end up being a little bit different and nicer, but I just want to let you be aware of that. So let's go ahead and look at letter F. And that'll be our last example for today. We're going from 1 to 1/8 to 1/27 to 1/64. Ugh. Okay. Well, I know that 8, 27, and 64, they are all perfect cube numbers. And I know I'm not adding the same number each time to get to my next value, so I know that this is not arithmetic. And I know I'm not, like, 1 times 1/8 is going to equal 1/8, but 1/8 times 1/8 is not 1/27. So that tells me that this is not geometric, so this is a neither. And what I see here is that 8 is a perfect cube, 27 is a perfect cube, and 64 is a perfect cube. So, and I also know that 1 is a perfect cube. I know that 1 cubed is equal to 1, and I know that 8 is equal to, I'm sorry, I know that 2 cubed is equal to 8, and 3 cubed is equal to 27, and 4 cubed is equal to 64. So it's like I'm taking like 1 over 1, and like this is 1 over 2 to the third, and 1 over 3 to the third, and 1 over 4 to the third. So where does the 1, or this is going to be to the third. Where does 1, 2, 3, 4 come from? Well, that is your position. So this is in the first position, the second position, the third position, and the fourth position. So what am I doing here? Well, it looks like our rule is our numerator is going to stay 1, since all of the numerators, even this one has a numerator of 1. It's 1 over 1 to the third. And my denominator is going to be my position to the third power. And that's my rule. There's nothing more that I really need to look at, and it is what it is. That is the end of today's lesson. If you would like to try some of these on your own before coming into class tomorrow, I think that would be awesome. Or what you can do is you can just wait till we get into class and collaborate with the people around you. But that is going to be the end of today, and if you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.